Good evening, everyone. Good afternoon or good morning, whatever time you are watching this. So this week we are focusing on motion in two dimensions. Again, I would, if you have the opportunity, you can take a peek at Khan Academy website. Go to subjects and science and physics and two-dimensional motion, and then you have a bunch of good videos. They are short and they are wonderful to give you a perspective of two-dimensional motion. Um, so let me browse through the chapters. So basically sections in our book, chapter 3. So motion in two dimensions means now we are dealing with x and y components, and chances are you have to have some skills in adding vectors. Let's say we have two vectors, vector A and vector B. We want to add them, and the way we add using geometry, you take the tail of the second vector and then you put in the head of the first vector, and then you connect the tail and head, tail of first vector and head of the second vector, and then you connect that. Okay, here is your resultant. So let's say in another situation you have not two vectors but you have three vectors, A, B and C, and you want to find the resultant sum of these three vectors. You use the same idea. You take one of the vectors, could be any of them. Let's take B. Here's your B vector, and when we do a geometric representation of a vector, it has to have the same magnitude. If it is a geometric representation, it means it has to have the same length and the same orientation, the same direction. So you take the first vector and then you bring the second vector, let's say A. The tail of it goes on the head of the first vector, and then you just transpose it. So here's my vector A. What I did, I took this vector and then I place it in here by connecting its tail to the head of first vector. And what I do next, I bring my third vector C using the same process. I take the tail of it, put in the head of second vector, and I bring it on. So here's my vector C. Same size and same orientation. So what is the resultant vector? Well, the resultant vector is given by connecting the tail of first vector to the head of last vector. Here's my resultant vector. So using geometry, that's how we do. So sorry about the little silence before. I am not used with this taping device yet, but okay, we should be doing now. Okay, so let's say you have your y-axis, your coordinate system, your Cartesian system, and you have a vector r that you want to project it along x and y direction. And this vector r makes a given angle theta with one of the axes. So what is the projection of it? What is Rx? So Rx, which is given by R projection in the x-axis, here's your Rx, is given by the magnitude of vector R, cosine of the angle this vector makes with the x-axis, and Ry is equal to R sine of theta. So let's review those functions, sine and cosine. So a triangle that has sides A, B, and C, where sides C and A makes an angle theta with each other, and this triangle is a rectangle, makes an angle of 90 degrees. The definition of sine of an angle is the ratio between the opposite side by the hypotenuse C, and cosine of the angle is defined as the ratio between adjacent side and hypotenuse. We might use tangent, which is the third function, is given by the opposite side divided by the adjacent side A. B over A. That's tangent. So that when you look at our triangle over here, which is made of projection Rx, projection Ry, projection of R in Y axis, and the vector itself R, then cosine of theta is our adjacent side by hypotenuse, and the sine of theta is the opposite side by hypotenuse. So it's the same idea, which allow us to quickly determine the projections of a vector in x and y direction. So this is the mathematics of it. Where are we going to find and use this type of properties? Let's say we have a Google map, and instead of x-axis we have the eastern direction, the north direction. Of course, this is south, here's west. And let's say you have a mobile, some object that moves 100 kilometers in the due east direction, so 100 kilometers. And then it turn around and move north another 100 kilometers. And then we want to find what is the total displacement of this mobile. And displacement, as we saw in the video that I submitted last week, the displacement is given by connecting the last point by the origin, by the first point. So first is moving from origin O to point A, let's say a city A, and then from city A move to city B. So the displacement vector is given by position B minus origin O. So how do we find the size of this displacement? Well, we have to remember our Pythagoras ruling. So we have a right triangle. One side is 100 kilometers, the other side is 100 kilometers. So the hypotenuse is given by square root of 100 kilometers square plus 100 kilometers square, and that is 100 kilometers square root of 2, whatever unit is we are dealing with. Okay, For instance, in this example right here, we have an object that leaves the origin and go northward 20 kilometers due north, and then it turns around in the direction 60 degrees west of north, and then moves B displacement, which is 35 kilometers. And then we want to find the total displacement of this body. So we have this much by this much, and using the geometric rule, remember, we connect the tail of first vector to the head of last vector to find our resultant vector right here. Okay. So if we want to so in this exercise, that's how we solve using geometry. So let's say we want to find a real displacement and how many degrees, or what is the direction of that displacement with respect to due east direction. How do we find this? So let me show you how to do that. So we use what we are learning as far as projection is concerned. So we have our x-axis, which is our due east direction. Here's our y-axis, which is north, and then whatever motion we got is 20 kilometers due north, and then we turn 60 degrees, and then we all walk another 35 kilometers with an angle of 60 degrees, and we want to find, oops, my vector is all curved, sorry about that. We want to find r. We want to find not only the magnitude but also the direction. We want to find exactly which angle is this one over here. What is the angle of our displacement vector with respect to this due east direction? So how do we do that? So the way I recommend you to do is to build a little table. And in this table, you write down all the vectors you wanna to sum. And so here you write vectors, and here you write what is the actual x projection of these vectors, the y projection of these vectors, and then you just list them. This is our a vector, the one that goes due north 20 kilometers, this one over here. And the other vector we want to sum, the b vector, is the one that turns 60 degrees west of north, this one over here, right? We want to sum those two vectors. We want to find a resultant, right? So, but to sum, we sum projections. Don't forget that. So how do we do that? So our vector A, how does vector A project in this x-axis? So vector A projects as a dot, right? So if you take this vector and collapse it onto x-axis, we get nothing. We get zero projection. And how does A project in the y direction? Well, it's entirely there, 20 kilometers. Correct? So how does vector V project in x? Look at this. When I project my vector B in x, when I project it, when I take it down, this vector will have a direction. This direction opposes the direction that I'm calling positive. So which means this projection will have a negative sign. A negative sign. It's very important that you consider all the signs in a correct way. So it's a negative sign. Now the other thing you must know is, well, we just learned about sine, cosines, and how can we use sine and cosine to find projections. So this angle, if this angle is 60 degrees, we want to project our vector b onto x-axis. Let me extend the x-axis right here. We want to project vector b onto x-axis. We know this angle is 60 degrees, so this angle down here is 30 degrees. 30 degrees, correct? Because 60 degrees plus 30 degrees is 90 degrees angle. 90 degrees angle, correct? So this is 60 degrees. So the projection of b onto x, first of all, will be negative because it's oriented in the negative direction, but is also equal to b cosine of 30, as we learned in the previous the previous screen. And the projection of b in the y direction, this one, the projection will be pointing in the positive direction, so it's going to be plus magnitude of vector b, which is 35 kilometers, sine of 30. Okay, so what is going to be the projection? So when we sum the projections in x, we're going to have negative 35 cosine of 30. And when we sum in the y direction, it's going to be 20 plus 35 sine of 30. So therefore, our x is equal negative 35 cosine of 30, and Ry is 20 plus 35 sine of 30. If we want to find the angle it makes with the x-axis, so this angle over here is 180 degrees minus this angle. I'm calling 5. And 5, the angle 5 is one whose arc tangent is equal this much, which is our Ry, divided by this much, which is our Rx. So then we go we bring our calculation and we calculate cosine of 30, square root of 3 over 2, and Ry 20 plus 35 sine of 30, which is half. Okay, and then we have the problem solved. Motion in two dimensions. There are several. We can do as we did in the previous chapter. So we have a body that goes north 20 kilometers in 2 hours, and then turns around and go 35 kilometers in certain amount of hours, right? And then we want to find the displacement. So that's one type of motion, and another one is called the projectile motion. So projectile motion is a motion in which, again, we have two components. We have a component in y, we have a component in x, so what I'm showing here, sorry, I was talking about projectile motion, but before going there, let me show you this motion. So you have a red ball, it's moving a circular path, and we are looking down on it. So this green vector here is the velocity vector, indicates the velocity vector, is always pointing along the path, along the direction in which the ball goes, and the blue vector attempts to represent acceleration. So this is a type of motion, is a circular motion. The speed seems to be constant. The speed seems to be constant. The velocity vector, the magnitude of it, which is speed, seems to be the same always. So the velocity is constant. But look at this, you do have an acceleration. Okay, so velocity, the magnitude of velocity vector is constant, meaning the speed is constant. But the velocity vector itself is not constant because its direction changes all the time. So remember the definition of acceleration. Acceleration is such that the change in velocity over time is different from zero. And then you have an acceleration that is not zero. So is the magnitude of velocity vector constant? Yes, the speed is constant, but not the direction. Therefore, the velocity itself is changing, meaning we do have acceleration. Let's show you in the case of a linear acceleration or a linear motion. So the same thing. Blue is acceleration and green is velocity. So you have two situations here. One is there is a speeding up process and a slowing down. Notice one thing. When the ball speeds up, the velocity vector and the acceleration vector, they both have the same direction. Notice that? Right now. Not now. Right now they do, and not now. So when the ball slows down, the acceleration and the velocity vector, they both point in opposite direction. See that? So this is one of the main learning process in linear motion, in motion in one dimension. When the velocity vector and the acceleration vector, they both have the same sign, either positive or negative, you have a speeding up process. And when the velocity vector and the acceleration vector have opposite signs, you have some slowing down process. Let's show now an example of projectile motion. So a projectile motion is one in which you describe it by a y-x component and an x-axis component. So at any given moment, oh wait a second, should I put sound? Ooh! Okay, so I can put some. Okay, in a projectile motion, when I launch the projectile, as the projectile is anywhere in its path, I can project the position of this projectile in my y and x projection, right? Y and x axis. So when I do that, here's what I learned. So here it is. As that projectile goes up, at any given moment you can project the position of that projectile in the x component and the y component. And what do we learn? Well, we learn that the velocity v, when projected along this line, along this line gives a constant value. See the size of this vector here in x is always the same. As if when the projectile goes up, if you were to run right underneath it and look it up and make sure you stay in sync with it, you would be running with a constant velocity. Let's go back to the simulation. So in this example here, if you place this dude, I cannot do that properly, but if you place this dude in such a way that this dude stays right here, right? And once he throw the cannonball up, he fire. If he could run right underneath the ball, he would run with a constant velocity as he look up and see the ball going up and down. See that? So if he could go running along this line and look it up, make sure he's always under the projectile, he would be running with a constant velocity along the x direction. But in the y direction, which means if he had an elevator that would move him up and down, trying to be in sync in the y direction with the ball, his motion would be one with an acceleration. Not only that, he would be in a free fall type of motion. He would go up with an acceleration 9.8 and down with an acceleration 9.8, in both cases with this acceleration vector pointing down. Okay. So when we study projectile motion, here's what I recommend you to do. You have three types of motion. We have one in the x projection, and you have another one in the y projection. And the motion in the x projection is such that position is equal to Vx times time. And in the y projection, the way you describe is such that use the same equations of motion we learn in free fall motion. Remember those? The second one and the third one. Okay, and I'm sorry, and what is V naught in the y direction? What is V naught in the y direction is given by this. Let's say you have a projectile that is launched with an angle theta with respect to the horizontal. So this projectile has an initial velocity V naught. So what you do before you start your problem, you make a little triangle listing your V naught, your V naught x, and your V naught y. And here's your angle theta. So that V naught x is equal to V naught cosine of theta. And V naught y is equal V naught sine of theta. So this is the effect of V naught x. Okay. So projectile motion is this, and with these I will probably stop this outline of chapter 3. Here's what I would like you to do. I'm not receiving a lot of requests and email from students. Let me check WebAssign. Yeah, just checked WebAssign. WebAssign of chapter 2 is not well explored. And these assignments will be closed on Monday, in fact tomorrow. So students, you guys have to work hard to get them done. Okay? So out.